Alright, now we get into some more little fun, quirky questions. The statement reads, on the basis of the naive model presented earlier, estimate the magnetic susceptibility of a diatomic metal such as copper. Compare your answer with the empirical value in the table and comment on any discrepancy. Alright, well, at least we know what we're getting into with being a naive model and all that. So if V is the volume per electron, then we say that the magnetization is equal to the little magnetic dipole per volume, right? This is a straightforward definition. But this is equal to E squared R squared over 4 ME, the mass of the electron V, times B, the magnetic field. All right, but M we also know is equal to chi M H, which is equal to chi M over mu naught plus, or times 1 plus chi M B. And if we distribute through, since chi M is relatively small in the denominator, so 1 plus that leads to 1. This is approximately equal to chi M over mu naught B. Note that chi M is much, much less than 1. Kind of already figured that. So the approximation of 1 plus chi M is approximately 1. What this allows us to do is set these things equal to one another and solve for chi M by multiplying over by mu naught. Okay, now this field here was given by the Bohr model. Rough, crude, and only really works for one electron. But we can apply it here. Let V equal the volume of a sphere, so 4 over 3 pi r cubed. And we'll let R equal 1 angstrom, or 10 to the negative 10 meters. Then we can say here that after plugging in and substituting in the volume and canceling, we get that chi M is equal to negative mu naught over 4 pi, 3e squared, 4 MER. So let's just plug everything in. The mu naught over 4 pi is equal to 10 to the negative 7, kind of by definition designed that way. And then we have 3 times the charge of the electron divided by the charge of the mass of the electron and the radius. And that yields to negative 2 times 10 to the negative 5. But the table says that copper is about negative 9.7 times 10 to the negative 6, or negative 1 times 10 to the negative 5. So at least we're in the ballpark, but we definitely have a crude estimate based on what the Bohr model gave us. So in conclusion, this approximation isn't bad considering the use of 1 electron per atom density when copper has 29. That's the big difference there. And a very crude value for R. Since the orbital radius is smaller for inner electrons, they count for less, but still close. So again, we can still get in the ballpark, and based on application, we can get more specific as needed.